9.6 is really going to tie together a lot of what we've been doing in this chapter. So we're going to talk about vector and parametric motion on a curve. We're going to be looking at particle movement. But really, this section is just a review of a lot of things from earlier sections tied together. So you'll notice there's no info box at the beginning, there's no new formulas. What we're really doing is applying what we know into new situations. So I actually really encourage you to pause the video, and before we even start, to take a look over problem number 1 here and see if you think you can find any of these solutions on your own. And then unpause the video and walk through it with me. Okay, number 1, the polar curve is given by r of theta equals 2 theta plus cosine of theta between 0 and 2 pi. And then we are being asked on part A to find the area in the second quadrant enclosed by the coordinate axes and the graph of r. So we are being asked, let's go ahead and sort of identify what that area is on our graph. We are being asked second quadrant for this area here. Right? It's bound within the second quadrant, and it's under the curve of our identified function. So just like in previous sections, the first thing we probably need to do is find the bounds. So let's go ahead and do that. Find the bounds. On this one, we actually don't have to do too much work. Since we're in quadrant 2, our bounds are just going to be pi over 2, and ooh, that doesn't look like a 2. Let's try that again. Pi over 2 and pi. This is pi over 2. This is pi. We're going around this way to form that area. So those are the bounds that we need. The second thing we're going to do is we're going to just integrate to find our area. So our area is going to be 1/2 of the integral from pi over 2 to pi of our function squared, or of our r squared, 2 theta plus cosine of theta quantity squared d theta. And then this here is just a calculator problem. When you plug that into your calculator, you should get 13.338. All right, let's go ahead and look at number 2. In the quadrant, so before pi over 2, 4 theta between pi over 2 and pi, there is 1 point P on the curve, 1 point P on the curve with the r coordinate 4.218. Find the angle, so we're being asked for theta, that corresponds to that point. Let's do that part first before we even keep reading. So what we just said, and I'm just going to make a note, is that we're talking about r being equal to 4.218, and we're being asked to find theta. Well, we have r, and we know what r is equal to. R is equal to 2 theta plus cosine theta. So we can set that up. Then we're going to use our graphing calculator. So on your graphing calculator, I'm going to try and give pretty detailed instructions here. On your graphing calculator, in function mode, you're going to go ahead and graph y1 equals 2x plus cosine of x, and y2 equals 4.218. You're going to graph both of them at the same time, so you should get a function and then you should get a line, and what you're going to do next is you're going to hit second, trace, intersection, and that should give you the value that you're looking for theta. So let me recap that. On your graphing calculator in function mode, you're going to type y1 equals 2x plus cosine x. y2 equals 4.218. And go ahead and pause the video to make sure you're actually practicing this. Then once you hit graph, you're going to see a horizontal line and your curve. You're going to hit second, trace, intersect, which is probably down at number 5. And then it's going to say first curve question mark, and you're going to hit enter. Second curve question mark, and you're going to hit enter again. And then it's going to say guess, because apparently our calculator doesn't know it's pretty exact. You're going to hit enter again. And that's going to give you an x value and a y value. So you're hitting enter 3 times on your graphing calculator after you hit second trace intersection. And theta here is going to be your x value that you just found. And that's going to be 2.513 or 2.5136. So that will give you your theta value, right? Because x is holding the place of theta in what we just typed into our calculator. So we have successfully completed the first part of this problem, find the angle that corresponds to P. Now it's asking us to find the y-coordinate of the point P. Now, think about what we just found. Using this r value and this theta value, we came up with a polar point. And actually, let's give ourselves, actually, I'm just going to come down here and give myself some room. We just came up with the point 4.218, 2.513 in polar coordinates, right? This is our ordered pair in polar coordinates. This question, the second part of this question, is specifically asking us to find the y-coordinate of P. Well, how do we find y in polar? Y is equal to r times sine of theta. So in this case, that's 4.218 times sine of 2.513. And if you plug that into your calculator, you're going to get that the y value, I'm going to come back up here, is 2.480. So pause the video, rewind the video if you need a little bit of help there. And then we're going to go ahead and take a look at part C. So I'm going to erase all the work here so that there's obviously space for me to do part C. So pause the video if you need to. All right, part C. A particle is traveling along a polar curve so that the position at time t can be represented as x of t and y of t, such that, here we're going to get some important information, such that d theta dt is 2, find dy dt at the instant that theta is 2 pi over 3, and interpret the meaning of your answer in context to the problem. So a couple things I just want to note to myself, that in this problem we are being told that y is a function of theta, since we're looking at d theta dt, which means dy dt would be equal to dy d theta times d theta dt, similar to how we did this parametrically. Okay, now let's plug in what we know. We're being asked to find dy dt. We know that d theta dt is 2. So what do we need to figure out what is dy d theta, what is dy d theta at theta equals 2 pi over 3. So we need to find dy d theta at 2 pi over 3. That's what we're being asked to do on this question. Okay, well, y is going to be equal to r times sine of theta. And this is still a part of this big problem, right? So I'm going to rewrite, since we can't see it right now. We know that r of theta, this is still the same problem. This is our r of theta. So y is going to equal that r value times the sine of theta. So 2 theta sine theta plus cosine squared theta. Nope, not cosine squared theta. Silly. Cosine theta sine theta. If I just take this r value and I multiply it by sine, because that's how I find my polar coordinate, or my polar equation for y. So now I can take the derivative of this. That's going to give me 2 sine of theta plus 2 theta cosine theta minus sine squared theta plus cosine squared theta. Now this is pretty messy, and I could probably clean it up, but I only care about what is happening when theta is equal to pi over 3, 2 pi over 3. So I'm going to just go ahead and plug that in and simplify this, and you can do that on your calculator. You could do it by hand as well. When you simplify this, dy d theta at theta equals 2 pi over 3 is negative 0.8623. So now I'm going to plug in what I know. I want to know, we're going to come down here, I want to know what dy dt is at the moment that theta equals 2 pi over 3. And what I know is that dy d theta at that moment is negative 0.8623, and that dy dt at that moment and at all moments is 2. So I can just multiply this to get negative 1.742. You don't even have to do that. You could leave it just like this, because really to interpret this, all that matters is the sign. Is it positive or negative? So since dy dt is negative, less than 0 or negative, at 2 pi over 3, or at theta equals 2 pi over 3, the y value is decreasing. That's how we can interpret what this means. The y value is decreasing. All right, and then let's just come down here and create some space for D. I think I can fit D here. For part D, it says find the particle, for the particle in part C, so the particle we just found, if theta is equal to 2t for some time t, then determine the position, velocity vectors, the position and velocity vectors of our particle. So let's first define what x is. Again, using this r value, x is going to equal r times cosine of theta, so 2 theta cosine theta plus cosine squared theta. Y, which we already found up here, is 2 theta sine theta plus cosine theta sine theta. And we are now going to find the vector and substitute in the fact that we know that theta is equal to 2t. So we're going to find our position vector by substituting in 2t. So if I substitute in 2t for x, I'm going to get 4t cosine of 2t plus cosine squared of 2t. And for my y value, I'm going to get 2t sine of 2t plus cosine of 2t sine of 2t. And this, actually, I'm going to simplify, and I wouldn't simplify this if I didn't also need to take the derivative of this to find my velocity vector. But since I do, I'm going to simplify. I'm going to do the simplification part in green so that you can see it better. I'm going to use the double angle property to simplify this, which is just the same thing as 1/2 sine of 4t. That's just going to make it easier to take the derivative. You don't have to do that, and you could find the derivative. It's just going to involve more of a product rule situation there than a chain rule. So I guess that's sort of dealer's choice on your preference. But there is my position vector. And then the last thing this question is asking me to do is to find my velocity vector. So I'm just going to take the derivative. That's going to give me 4 cosine of 2t minus 8 sine of 2t minus 4 sine of 2t cosine of 2t. That's all my x-coordinate. Some product and chain rules happening here. Did not save myself enough space, so let's zoom out and move this over a little bit. Okay, and then my y-coordinate is going to be 4 sine of 2t plus 8t cosine of 2t. Okay, I'm going to come down here. I'm just totally out of space. Plus 2 cosine of 4t. So there's my velocity vector. Again, likely some of that could be simplified, but why simplify if we don't have to? And that is all that we need to worry about for question 1. So I encourage you to pause the video, flip over your paper, and see how far you can get on question 2 on your own. Then unpause the video and we can work through it together. All right, number 2, part A. The graphs of the polar curves r equals 3 and r equals 3 sine of 2 theta. So first of all, let's just go ahead and identify r equals 3 is this curve right here. R equals 3 minus 2 sine of 2 theta is this curve right here, are shown in the figure below from 0 to pi. Part A is asking us to find the area of R. So stop and think through your approach for part A. And I'm going to do the work for part A up here since there's all this space up here. So my approach, my first thought is that in quadrant 1, the entire graph is being formed by my green curve. So that means I'm going to be using the bounds in quadrant one. So quadrant one is all r equals 3 minus 2 sine of 2 theta. So I'm going to find that area, which I know will have bounds from 0 to pi over 2, since this whole area is taking place in the first quadrant. And I could check by plugging in 0 to get 3, which is my radius here, and I could check by plugging in pi over 2 to get this point here, just to confirm that for myself. But that is, in fact, true. I could also check graphing on my graphing calculator and make sure it's rotating in that direction. So I'm going to find that area first, and I'm going to add that area to the area of the circle from pi over 2 to pi. Or in theory, we could find the area of the whole circle and divide it by 4, since this is exactly 1/4 of our circle. But seems pretty simple just to do the integration from pi over 2 to pi. So let's set up our integrals. So 1/2 times the integral from 0 to pi over 2 of 3 minus 2 sine of 2 theta d theta. Don't forget your squared sign, and I should probably add a second set of parentheses here, plus the circle, so 1/2 times the integral from pi over 2 to pi of 3 squared d theta. Everything after this point is a calculator problem, and I believe you should get 9.707 when you evaluate each of those integrals and then add their values together. All right, part B, the distance between the curve is changing between 0 and pi over 2. So notice that's saying between 0 and pi over 2, this distance between one curve and the other is changing. The question asks us to find the rate, that's telling us to look for a derivative, find the rate at which the distance between the two curves is changing with respect to theta when theta equals pi over 3. So first, let's talk about the distance. What is the distance from one curve to the other? Well, the circle is the first curve. So the first curve, and the equation of that circle is 3. We're going to subtract out the other curve, right? Because 3 would go all the way to the origin. We're going to subtract out the other curve, which is 3 minus 2 sine of theta, to find the distance, sine of 2 theta, to find the distance between those two curves. The length can be represented in that way. Then what we're being asked for, and just to point out, this is just going to give us 2 sine of 2 theta when we do that. What we're being asked in this problem is we want d theta. We want to know how that distance is changing. So the distance is just one equation minus the other, how far away they are from each other. What we're looking for is the rate of change, which means we want d theta. Well, we can take the derivative of d here with respect to theta. That's going to give us 4 cosine of 2 theta. And then we are going to evaluate this when theta is pi over 3, which is going to give us -2. So the rate at which it is changing is -2. Part C, a particle is moving along the curve, r equals 3 minus 2 sine of 2 theta, so that d theta dt is 3 for all times where t is greater than or equal to 0. Find the value of dr dt when theta equals pi over 6. So let me set up just so that I can, for peace of mind, kind of figure out what it's going for. We want dr dt. How would I find dr dt? I would take dr d theta, and I would multiply that by d theta dt. That would give me dr dt, right? These would simplify out diagonally my d thetas. So we need to figure out what dr d theta is. Well, we know r is right here, so we can go ahead and take the derivative of that with respect to theta to find dr d theta. And that derivative is just going to be -4 cosine of 2 theta. And the moment that we care about in this problem is when theta is pi over 6. So if I plug that in, I'm going to get that dr d theta at theta equals pi over 6 is equal to -2. So I can substitute that in -2. I was given d theta dt in this problem. Right here, d theta dt is 3. So dr dt is going to be -6. And if there were units, we would need to keep that in mind. Since there aren't any units on this problem, that's not something I really want you to worry about. All right, I'm going to make some space so that we can look at D, but I do encourage you, if you have not already, pause the video and try and work through it on your own. All right, part D says a different particle is moving along the curve r equals 3. If theta equals the square root of t, then what is the velocity vector of the particle? So the first thing we need to do is figure out what the position vector of the particle is. In terms of t, then we can take the derivative of that to find the velocity vector. So x is going to be a function of theta. X is going to be 3 cosine of theta, using this as our r value. Y is a function of theta. Y is going to be 3 sine of theta. And then to actually find our position vector in terms of t, we're just going to substitute in, and I'm going to use theta equals t to the 1/2 power. So this is going to be 3 cosine of t to the 1/2 power, comma, 3 sine of t to the 1/2 power. So there's my position vector. And then I'm just going to take the derivative of that to find my velocity vector. And that's going to give me -3 over 2t to the power of 1/2 times, not cosine, times sine of t to the 1/2 power. So I'm using the chain rule here. And the derivative here is going to be 3 over 2t to the power of 1/2 times cosine of t to the power of 1/2. So there is my velocity vector. And last but not least, part E, what is the speed? What is the speed of the particle at the time that t equals 2? So we are looking, and we're going to use this same velocity vector. I guess it should have said in relation to part D. We are looking for the magnitude of the velocity vector at 2. So we're going to plug in 2 for all of our t values here. So -3 over 2 root 2 times sine of the square root of 2 squared. This whole thing is going to be squared, plus 3 over 2 root 2 times cosine of root 2, this whole thing squared. And that's a calculator problem from there. You should get that that is 1.061. So key ideas in this section, really just being able to do a multi-part problem. These questions are very AP-like in the sense that they're multi-part, they tie together, but they're assessing different things on different questions. And that really is where you want to be with this content. So making sure that you can work with polar, that you can work with parametric, that you can talk about the rate of change of different components in one problem. If you have any questions, go ahead and write them down, and I look forward to supporting you on this in class. Thanks for listening.